Hello, good morning. My name is Gustavo. I'm here to introduce our next guest speaker, Colin O'Brien, and he's going to be speaking about graphic-based detection and response.
All right. Hi, everyone. So as mentioned, my name is Colin O'Brien. I'm going to be talking about a project I've been working on for a couple of years now called Grapl. So Grapl is a graph analytics platform that really tries to target detection and response workloads, so finding and removing attackers from networks. Before I get started talking about Grapl, I want to give a little bit of context. I have been working in detection and response in some form of another for about 5 years now, my entire career. But I've had a lot of really different jobs in that time. I started off at Rapid7. I was hired by the Insight IDR product team, so that's their detection and response service. And my first job was basically to embed myself onto a data science team. So I was going to be the sort of security engineer for that team. And they asked me what I wanted to do, and I thought machine learning sounded cool, so they gave me that job. And what I found was that we did very little machine learning, ultimately. And really, we spent the vast majority of time looking at broken or just garbage data for whatever reason. Sources were out of date. Data would age really poorly, so security data in particular just ages really terribly, because you might think that like a virus scan happened a week ago, and that data is different from a virus scan happening a month ago or today. So I saw these security-minded data scientists digging into these massive data sets and really managing to pull tons of signal out of what looked like the worst kind of noise you could imagine. And I learned a lot about the techniques that they leverage, the tools, and the ways that they work together to do this. After about a year on that team, I started working on the IDR product more directly. So I worked on the detection team, building out attack signatures for our numerous different customers. These attack signatures had to work across pretty much arbitrary customer environments. You can never really predict who your next customer is going to be. They had to have low false positives, and they had to catch real attackers. I learned that the engineers who were building these detections leveraged code as their primary weapon. So all of the alert logic, the same way that our service code or any other code would have been checked in, it would have been code reviewed, it would have had unit tests. The sort of latter part of my time at Rapid7, which was roughly 2.5 years, I actually worked a lot on reliability, software engineering, and building services out. And so at the end of that time, I decided that I wanted to get a little more into detection and response. I wanted to stop being sort of the ivory tower vendor that looks down and hands down detections and actually do the job day to day. So I left Rapid7, I went to Dropbox, and for 2 years I was working on their detection and response team. So actually engaging with the red team and triaging alerts day to day, seeing what sort of problems were being faced. And what was interesting is that it was a lot of the same problems that I had seen in that vendor space. I saw security experts being tasked with dealing with what to me were data or engineering or operations problems, dealing with log sources that were incorrect or that weren't being parsed correctly, dealing with log volumes that they weren't necessarily in the right position to scale to. And so I tried to help that team out for about 2 years. And a lot of the lessons learned went into how Grapl works. One of the big things that makes Grapl somewhat more interesting than other products is that it is a graph-based system. And so today I'm going to talk about why I think that a graph-based approach is so important for security in general, but especially detection and response. And hopefully you can walk away with some understanding of why that's the case. Okay, so before I talk about Grapl, I think it makes sense to just go over what a graph is. So graphs are a data structure that comprised of nodes and edges. Nodes are usually things like entities or nouns, right? So a person might be a node. Edges denote relationships between those nodes. Graphs are a really powerful and generalizable data structure. And I think one of the easiest ways to demonstrate that is to take a really basic graph like this, right? There's almost no labels, there's no explicit data in a graph like this. But despite that fact, I can say a lot of things about this graph. I can say that the green node has a relationship with the blue node has a relationship with the purple node. The green node has a path to the purple node with a length of 1 that crosses over this blue node. The reason why I can say these things is because graphs have this really powerful property of encoding relationship information directly into their structure. This is why we see graphs used a lot in visualization, but these relationship-heavy workloads actually come up all over the place. So as some examples, Google Search is powered by their knowledge graph. And this is what allows them to, instead of taking just a plain text search approach to a search engine, start giving you related information. Facebook's Graph API underlies their entire public API. You can imagine why this would be useful. You might want to ask questions like, given a user on our platform, who are their friends? What are the posts that they like? And then we can recommend those posts to that initial user, right? This is another very relationship-heavy query. Graphs are in some more niche areas. So graphs underlie machine learning libraries like TensorFlow. TensorFlow is an example of something called data flow programming, where the computation that you build in your tensor graph is represented as a sort of graph traversal. And then graphs also tend to really just emerge from systems without any purpose, right? We end up building graphs without really meaning to. And an example of that would be BGP and the internet, right? You have all of these routers acting as nodes with neighbors that they know how to talk to. And that's how packets manage to get from one system to another, traversing this massive graph of the internet. A little closer to home in the financial security space, graphs have been used to great effect for quite a while now to detect things like credit card fraud or scam businesses. And they do this by querying and building models on top of these graphs to understand things like commonality about locations that credit cards are used, which users have in the past worked with a business, and then why is this new strange user talking to this business? And they're sort of a staple in that world at this point. In the information security world, we're starting to see graphs gain a lot more traction, unsurprisingly, given all of these other communities that have been leveraging them. John Lambert at Microsoft wrote a post a couple of years ago about his opinions on graphs in InfoSec. And in this post, he makes a statement which many people may have heard at this point. He says, defenders think in lists, attackers think in graphs. As long as this is true, attackers win. And in this post that he creates afterwards, he talks about an example of this list and graph-based thinking. John talks about how when defenders are tasked with protecting a network, one of the first things they'll do is start creating lists. They'll create lists of privileged users like domain admins, or exposed services or high-risk assets that contain maybe user data. And they'll start to prioritize the work that they do based on those lists. This is really different from how attackers go about doing their work. Attackers are going to opportunistically land on some asset. They'll compromise whatever they can, probably something unprivileged and exposed. And they're going to leverage the capabilities that they gain from that asset to start moving around your network. And this can range from things like lateral phishing, where an attacker might compromise your coworker's email, and then they'll send you a PDF and say, like, hey, look this over. And all of a sudden, they're taking over new users and assets on other people's computers across your network, or as John talks about, using tools like ProcDump or Mimikatz to dump credentials from memory and start moving around laterally. And what the attacker is really doing here is they're abusing trust relationships, right? The attacker is starting off on this network. They don't have these lists of users or assets ahead of time. They don't know these risk prioritizations. They're doing discovery. They're moving across the network in a very graph-oriented way. At the end of his post, John says, manage from reality because that is the prepared defender's mindset. And so I think there's kind of a deeper meaning here. At least that's something that I draw from this post, which is not that graphs are necessarily better than lists or lists are better than graphs or anything like that. It's really that when you have information that so clearly maps to one model, one data structure, and you force that information into some other model, you lose something inherently, right? So when we as defenders take graph information like a network or like how an attacker behaves, and we pull that out and we force it into lists, we lose actually the most important thing, which is what the attackers are taking advantage of, those trust relationships. One tool that I think really demonstrates a shift in approach is Bloodhound. Bloodhound is a tool that both attackers and defenders can use. And I think that really goes to show that it's sharing this common model. Bloodhound allows you to query and visualize Active Directory as if it were a graph. And from a defender's point of view, this is much closer to how attackers are thinking about and taking advantage of your systems. And this allows you to move away from asking questions like, who are my domain admins and how do I protect them? And instead start asking questions like, how would I go from an unprivileged user to a domain admin? And start cutting off those paths. Another tool that I think demonstrates this in a different way is CloudMapper. This is built by Duo and Scott Piper. CloudMapper is a tool that allows you to visualize and graph out all of your AWS resources and policies, and this lets you move away from thinking about individual policies and how they might have individual issues or they might look fine when you're just glancing at one of them. But when you start to combine them together the way an attacker would, as they chain attacks across different assets in your environments, you can start to find privilege escalations or leaks that you didn't expect. So in the detection and response world, the model and the primitive that we leverage is the event. And we do this by collecting logs, which are some sort of representation of these events. Things like process execution logs, file creation logs, network instrumentation, that sort of thing. What we do is we collect billions of these every single day, and we store them in what is effectively a massive index or a big list called a SIM. And we run queries against these, and we look at things like individual events as they occur, and we try to write queries against them to find something suspicious. If we do find something suspicious, we go back to our SIM, we write subsequent queries looking at more logs. The thing is that when you take some of these logs down and you know what you're looking for, you can start to see that there's actually a lot of relationships hidden in between them. A process ID in one log might be a parent process ID in another log, a file name might be shared across them. And when we start to pull these relationships out and make them more explicit, I think that we can start honing in on more complex attacker behaviors rather than isolated events as they occur across our environment. And so Grapl really tries to demonstrate what we've just seen. It tries to demonstrate that when we can move from thinking about logs as our fundamental primitive and instead more as a building block into an abstraction that matches what attackers are doing more closely, we can be a lot more effective as defenders. So Grapl will ingest raw logs. You can send it up sysmon or any other data type that it supports. It's going to parse those into a graph representation. So a process execution log might generate a graph that has a parent node, a child node, and an edge between them. These graphs go through an identification process. I'll talk a little bit more about this later, but essentially what this means is that we don't want a million different nodes representing the same entity, right? If we have 1,000 logs coming up about Chrome doing some action, we really just want one node for that Chrome entity. So that's what identification is going to do. These identified graphs get merged into Grapl's master graph. So in real time, as these graphs are generated, they're getting pinned up into this massive graph database that's going to represent all of the entities and behaviors occurring across your environment. And as this is happening, on every single update to this master graph, Grapl will orchestrate your attack signatures, or what it calls analyzers. They're going to look for behaviors. They're going to look for suspicious patterns. And when they find these patterns, and you've deemed this a risky enough situation to start investigating, you have a tool that's really going to exploit the ability for graphs to pull in context quickly, right? Everything's joined together sort of inherently, and Grapl calls that an engagement. And so I'm going to talk about how all of these things work, both in terms of a sort of generalized graph-based approach, and then how Grapl implements it. When I talk about the master graph in Grapl, it's really what you see here. There's actually more nodes than just what's here, and there's also a sort of plugin node, so you can add your own models. But nodes are pretty much what you would expect. They have properties, so a file has a path, a process has a process ID or process name, and then there are these special properties, the edges, right? So a process has children. A process can create files, network connections will connect out to their destinations. So identity is really important, not just to Grapl, but in general. It's why tools like sysmon try to package identities for things like logins or processes as baked into their process as is possible. Grapl is going to do something very similar to Sysmon, but it's going to do it on the back end. So it's going to be generalizable to really any source type that you send up. And it's going to provide an identity for every single node type. So not just processes, but users, files, network connections, anything that it can understand as a node. The problem with logs without identity is that you might see information like we have here, right? 3 events, they all share a process ID across some series of time. You might think that this is all referring to the same entity, but that's not necessarily the case. Process IDs can be recycled, and they're recycled actually really with quite a good amount of frequency. So if you don't have some way of resolving this, it's going to be really painful in any kind of investigation. So Grapl is going to use context from these logs, the timestamps, the event metadata, to disambiguate what these entities are and provide a canonical identity. When you combine that identification process with the graph-based approach, you can go a lot further than something like an instrumentation tool like Sysmon. We can coalesce all of that information that comes up across thousands of logs onto just that one entity, that one node, using its node key, which is the identity, and we can throw away a lot of redundant information. So this helps Grapl scale sublinearly. So you might send 1 million logs to Grapl. In my experience, across 1 million logs, maybe 10 to 30% of that information is actually unique. The vast majority of it is just the same thing over and over again, the same logs containing the same PID, process names. If it's something like Sysmon, they're really, really heavy, so it's going to have the process GUIDs, it's going to have parent process information. We can get rid of a lot of that in Grapl. And this can compound really quickly. So if we have a master graph with just a single node, it's got a PID of 100, and an event comes in, and there's a process execution where PID 100 executed a child process. We can immediately throw away some information, right? We can throw away the PID, and then that type information is actually encoded directly into the graph. If the child process creates a file, again, we're throwing away more and more information. And if that child process then reads that file, you can see how this really quickly compounds. We're storing almost none of the information in that log. We're just adding a new edge with a timestamp. This really goes towards a lot of what I've seen in the field as people fighting with their data. I see this in security. I see this in really every discipline where you're dealing with a large amount of data. Scaling linearly or worse with your data sets, it puts you in a position where you have to start throwing data away every year, or you have to ask yourself, do I really want this data source? And I don't want people to have to ask that question. I want you to be able to put as much data in this thing as possible. Okay, so detection is really what I think in terms of a log-based approach, SIMs and logs push us in the wrong direction. So I see a lot of detections that are looking at properties of an attack. The reason for this is that it's a little difficult to look at multiple logs, especially across log sources in most tools today. And logs don't really tend to encode a lot of behavioral information. They tend to just have properties. This makes logs pretty good for things like searching for hashes or IP addresses, like those low-level pyramid of pain IOCs. But when you want to actually talk about attacker behaviors, they start to fall apart. Joining these logs together is usually pretty difficult. So what I end up seeing is people building signatures based on attacker-controlled information. If I want to ask the question, where is exfiltration happening on clients, I can't really represent that in a generalizable way using logs, at least not very well. What I'll end up writing is something like, curl and wget are used for this a lot, and these are the command line parameters that I expect, and if I see these file names show up, then that's my signature. But that's really, really brittle. Every aspect of that signature that I've written is based on attacker-controlled information. And I see these signatures all the time, not just for exfil, really for everything. And so you might try to put some globs in there or use multiple queries with ORs and build this kind of monster query that tries to be robust. But ultimately, I think it's a losing game. One way of demonstrating this is if we take 2 process execution logs. This is Word and PowerShell executing. And there's no properties to go off of, right? Maybe if the PowerShell log had command line arguments, I could play that losing game of trying to parse them and say oh, this base 64 encoded data being passed in is suspicious for whatever reason. But as I said, that's attacker-controlled information. That's not what we want to focus on. Similarly, Word and PowerShell are benign digitally signed, valid programs, right? They're executing in the vast majority of environments, and they're doing so legitimately. So we can see here that logs are hiding what I would say is the most important piece of information. We have this PID sort of implicitly joining these logs together, and we can see that it's got nothing to do with Word or PowerShell executing. It's really that Word and PowerShell are executing together, right? There's this relationship between the two that we don't expect. And we want to start focusing more on behaviors and relationships as opposed to isolated events and properties. And we can generalize this further. It might not be Word, it might not be PowerShell, right? There's a number of ways to get code execution on an endpoint. It might be Excel loading a macro, it might be Adobe Reader getting owned, right? And they might shell out, or they might call into a JavaScript or Python interpreter on your system. And so what we really care about is tracking the fundamentals of what attackers do. Attackers execute processes. We should be tracking that sort of information, not trying to hone in on overly specific signatures that attackers can almost accidentally bypass. When we start to represent our attack signatures as graphs, and when we stop trying to deal with specifics of attacks and start to think more in terms of fundamentals, I think we can represent attacks much more creatively and much more powerfully. We can still leverage properties. So as an example, we might still want that signature for Word or Adobe Reader or Excel, these commonly targeted applications with non-whitelisted child processes. We can leverage that just fine. Graphs expose properties perfectly well, but we can also start asking much more complex questions like, what are the dropper-like behaviors in my environment? A dropper is something that I've defined as having a process that has reached out to an external network, creates a file, and then executes that same file. We're talking about multiple composite behaviors. You would have to probably join at least 4 or 5 logs from different source types, combine them together, and then analyze them in a sequential order, right? But in a graph, this is really straightforward. So what I really want to do here is basically start painting our master graph with risks. We want to start labeling our massive data set. And anyone who's done data science work knows that this is essentially the entire job. You start off with some murky data set, you get it into a clean format, and you start labeling it. And so for that, I would introduce the concept of risk. Another problem I see with security teams is drowning under false positives. It's a losing battle of constantly whitelisting. Anyone who's done security at a tech company in particular will note that developers and attackers do almost exactly the same things every single day. Their motivations are basically the only thing that differs. You will have developers scanning your network. You will have them basically doing privesks all the time, running Python, running things you've never seen. And so we don't want to have to constantly be chasing down developers doing their job. Instead, we can start to model things in terms of a risk gradient. I can say unique parent-child process, that's a low-risk event. It's definitely something an attacker does. I want to track that, but it's nothing like that commonly targeted application one. That's a much more finely tuned detection that I'll probably try to maintain a whitelist for. So what we have here is what I would call local correlation. These are tightly coupled attack signatures, but we want to take this labeled information and feed it into a model. And that's not going to be a machine learning model. It's just a way for us to view these risks together and get a sort of arbitrary level of correlation. And so here I introduce the concept of a lens. This is actually inspired by a talk by For, who's the CISO at Uber. He gave a talk in 2012 where we talked about sort of an arbitrary correlation lens. And so I really like that idea. I built it into Grapl. And the idea is that you have these correlation points, like an asset, a user's laptop or their username. And through that lens, you can view all of those otherwise disjoint risks. And now I don't have to write signatures like a unique process, parent-process relationship with a unique network connection. I can write those individually, view them through a risky lens like the asset, and see that they overlap automatically. And now we can build a risk score that takes all of this into account. And risk in Grapl is very simple. There's no fancy statistics. It will count all of the risky nodes and take the sum of their scores. And for every node that has an overlapping risk, right, it's involved in more than one risk at a time, we add an increasing percentage. So 10% for the first node, 20% for the second, that sort of thing. And what this is going to allow us to do is push things like, silly anomalies like a parent-child process that just happened to be unique, but it's an update that just happened on a computer. And those are going to fade into the background, and all of the risks that correlate together are going to start lifting up a lot higher. The way that these signatures are represented is in Python. My experience with all of the various domain-specific query languages out there is that they were built for one specific purpose, and as soon as you try to move away from that, you start running into problems. So a lot of the time, they can do things in 1 or 2 lines that's really, really cool and powerful, and then you want to do something like a join, or you want to really do anything that it wasn't designed for, and you're going to start running into like huge performance barriers, correctness problems. You'll run into the query sizes exploding and that sort of thing. So Grapl just uses Python. It's general purpose. Python is adopted by data science, security communities. I have confidence that if in 5 or 10 years attackers start changing up their tactics while other query languages might start to falter, Python's going to be able to scale in expressivity to whatever they're doing. And so this is what an analyzer in Grapl looks like. Here we have that commonly targeted application. This is a process query where we're saying it has one of these process names and any unconstrained child process. We have no whitelisting on the child processes right now. Grapl is going to take that query. It's going to do client-side query optimization. It's going to ensure it executes in constant time. So it doesn't matter how much data you have. These analyzers will always run in real time, in constant time. They'll be batched up, parallelized. Does a ton of work to make sure that you don't have really painful operations work to deal with. And if this signature ever hits, that onResponse method gets called next. The onResponse method can do things like contexting, as I'll show in a minute, or subsequent alert logic. But really, it's just going to label the data with some kind of a risk and a name. I think where Python starts to really show some power is when we want to do things that are a little more out there, like it sounds silly, but counting efficiently is not something that I've seen a lot of existing systems do very well. Here we're leveraging a parent-child counter abstraction, and this provides a specialized interface. It hides things like caching. The vast majority of the time, this isn't even going to hit our data lake, so it's going to stay really nice and efficient. This signature here is looking for living off the land type attacks, so processes with parent processes where the process binary is in system32 or syswow64. We're going to look for any execution of processes that match that. We'll use our parent-child counter abstraction to say, has this happened a few times or less? And if it has, that's going to be something that we want to track. I think probably the best part about using a standard tool like Python is that you get to follow standard practices. If you were to Google your SIM's name with unit test, you would probably not find great results. If you found any, they would probably tell you that it's just not supported. At least that is what I have repeatedly found. You contrast that with Python. There's a number of tools for making Python correct. There's linters for style. You can put it into code review and store it in GitHub. You can gate that on GitHub. You can run things like MyPy, so Grapl is statically typed, so you can avoid errors before it ever runs. And most importantly, you can just import the unit test library from the standard lib and write unit tests for your alerts. So when you're whitelisting or you're tuning over the next couple of years, when the people who wrote the alert are no longer there and someone else is maintaining it, they can be confident that their alerts and their detections are still working properly. I see this as a really significant problem at a number of companies. They have hundreds, I've actually seen thousands of individual detections, and they don't actually have a good way of determining that those work. They might have some end-to-end like attack system that tries to test the entire pipeline, but like coming from a vendor, we just wrote unit tests, and so I wanted to kind of give that capability to the average security team. I think investigations are probably where log-based systems really start to fall apart, to the point where attackers take advantage of it. And so I'm going to do sort of a straw man investigation of an attack using a log-based system. So as the incident responder, I come into work, I've got an alert, and there's some process execution log, and it went off because some threat intelligence feed has told me that the hash is evil for whatever reason. It doesn't give me much other information. So in a situation like this, there's usually two things that I want to do. First, I want to just quickly see what has this process done. I'm not going to do like a fully scoped thing. That's something that I would bring the rest of the team in for. So I'll just see what it's done, and then I'm going to trace it backwards and try to find where this thing came from. So I'll open up a search window, probably like 4 or 8 hours, depending on when this thing happened. I'm going to look at like the last business day or so. And I'm going to start pivoting, right? I want to take information that I have, and I want to gain new context, new data. So I'll search for the PID, because I want to see what this process has done. And I get all these logs back, right? And some of them are interesting, and some of them tell me that this thing maybe shelled out a couple of times. And this is notable enough that I'm not immediately discounting this as being benign. So I'm going to start tracing it backwards. And I'll search for that parent process ID. And what I get back is a ton of logs, because the parent process, it turns out, was something like cron or launchd or scheduled task manager, right? What this tells me is that the attacker has probably been on this asset for weeks or months, and they scheduled their final payload to execute in the future because of this exact workflow. They know that this is going to really mess with me, and so that's why they do attacks like that. They know that the data that I'm looking at is going to be severely disconnected in terms of time from the data that is going to tell me where this attacker actually started off. So at this point, I've hit kind of a dead end with processes, so I have to pivot off of things like the hash or the file name. I want to see where this payload was actually created. I don't get anything for the hash, and I don't get anything for the file, right? Clearly, the attacker is outside of my search window. I really only have one choice at this point. I'm going to extend my search window out. And this might be days if I'm lucky, more likely weeks. And if I'm really unlucky, they've been here for a couple of months. This is starting to give me the results I want, right? I'm getting the image name creation maybe, but I'm paying really serious prices here. For one thing, if I've extended my search window from 4 hours to a month, every single search from this point forward is going to be hundreds of times slower. I could try to play the game of managing a whole bunch of different search windows and like 10 different tabs, but there's just no winning with a system like this. What's worse to me is that I'm probably going to start running into PID collisions. So maybe you're lucky and your entire investigation can be done with something like sysmon using process GUIDs. That's never been my experience. Even on Windows systems, I end up looking at the event log. I end up looking at something that has a PID without a process GUID. And PID collisions will happen over this period of time. For a client laptop running any multi-process architecture program like Chrome or Firefox or all sorts of things at this point, users are going to reuse PIDs a number of times in a day. So when we're talking about weeks or months, I will have many PID collisions to resolve, and that's going to suck for me. It's going to really slow things down, especially coupled with those slower search times. A third problem that's a little harder to see is that the fundamental thing I'm trying to do here is pivot off of my data, but I don't really have clear questions. I'm sort of just doing like raw text searches for whatever information I have. And I could try to constrain those by searching specific fields, but it's just very murky in terms of what I'm looking for and what I'm getting back. So Grapl takes a really drastically different approach. And at the heart of this approach is the Jupyter Notebook. So this is, again, me stealing ideas from the data science community because they've been doing this sort of work for years. And it seems really silly that we wouldn't look at what the experts in data analysis are doing, right? That's a huge part of this job. And what they're doing is they're using Jupyter Notebooks. These are these sort of super-powered Python environments. So if you've ever opened your terminal and typed in Python, you may have started writing code, and it gives you some immediate feedback, right? These are a lot like that, but you can organize your code into cells, replay them, modify them. You can also do things like shell out to the command line really easily. You can embed images, markdown, and these are sort of the tool of the trade at this point for investigating large amounts of data. We're starting to see Jupyter Notebooks in security a little more, so I believe Azure Sentinel is pushing notebooks as how they want people to do investigations. So it's definitely gaining traction as an idea. So I mentioned those lenses earlier. So as the incident responder, looking at your Grapl homepage, you'll see a list of lenses, right? And these are going to be your correlation points, so different assets or usernames. And we're just going to see which one is riskiest. And I don't have to worry about having 1,000 false positives. I have a set number of hours in the day that I can put towards incident response, and I'm just going to apply that to lowering the risk as much as I can, right? And I think this kind of goes towards Flea's talk a little bit as well. You don't want to be spending all of your time gatekeeping and hammering things down. You want to just sort of manage risk. You want to move towards a risk management approach. Otherwise, you're going to burn out your on-call. So if we click on one of these lenses, we get a graph. This is going to, in this case, contain 3 nodes with some relationships between them. We can click on any of these nodes, and we can see any of the properties for things like these processes or files or anything that's in here. This is a pretty data-rich graph. This may have taken, in this case, probably tens of logs, so probably like more than a browser screen worth of logs. But because we can coalesce all of that data with that identity, we can create a very dense and compact representation. If we click on the command.exe here, you can see that the analyzers involved are that we've never seen anything called dropper execute command.exe before. So there's a signature in Grapl that just looks for unique parents of command.exe, right? That's a pretty fundamental thing that attackers do. They shell out. Anytime you're in Python or another language and you try to p open, it's going to go through a shell. And then we have a much more constrained signature, which is that we maintain a whitelist of valid SVC hosts. Attackers like to pretend to be legitimate services like SVC host. And so we're just going to track that sort of thing. And thanks to the lens, these automatically overlap, and we get this cumulative risk score. So in my Jupyter notebook, I'm going to create an engagement. Engagements are like a special type of lens where you control what nodes are brought into it. And I'm going to pull in that first node. I'll pull in the SVC host, right? And I'm just going to pull it in by its identity. And this is in the Jupyter notebook. So you would probably have 2 browser panes or even 2 monitors, one with the Jupyter notebook and one with your live updating graph visualization. At this point, pivoting is really efficient and really simple. I don't have murky questions. I want to ask what this process did. So the first thing I'm going to say is what children processes were executed from it. This is extremely efficient. There's no search windows to deal with. It doesn't matter if these 2 processes occurred across wildly different timelines. This could be months apart. It's going to be a constant time expression. It's going to pull it in milliseconds. So I say get children or get the parent process, in this case, to start expanding it out. And that pivoting is nice and efficient and clear. So to sort of replay a similar situation as before, we would start off with our Jupyter notebook. We have this sort of root of our investigation, right? That's our SVC host. And we're going to just do our pivoting behavior, right? I want to find out what has this process done. I say get the children processes. Immediately, that's going to show up in that graph visualization on the left, as I'll show you. And it's also going to let me display and play with the information in the notebook itself. So I know this thing is probably not great. It's shelled out 3 times. That's pretty sketchy. I'll do that pivoting behavior again. I'm going to climb backwards up the process lineage, right? Really simple, really efficient. We can see that there's a dropper.exe. We can see that there's this chrome.exe. So this is telling a really simple story, right? A user was probably phished through Chrome. They executed something called dropper. That dropper, if we were to expand this out further, reached out to S3, pulled it down, and all of these logs are available for you guys, as I'll talk about later. And we're going to have this graph that looks something like this. Now, this graph, again, is going to contain probably tens, maybe low hundreds of logs worth of data. This amount of data would probably take up multiple pages in your sim to go through. But here we have a really nice compact representation. So you end up with a workflow that looks a lot like this. At the end of any investigation, you will have 2 really powerful artifacts. You're going to have, on the one hand, a graph visualization. This is going to be really great for showing teams that don't want to pour through thousands of logs. You probably want to interact with other security teams. You might want to show an executive or a manager, depending on what's going on. They're not going to want to look at logs. Graphs are nice. They're compact. They're visual. And even like a big attack across your environment isn't going to be too unruly of a graph to visualize. The other thing that we have is our investigation, and it's in code. And the fact that it's in code opens up tons of potential. The obvious one is that we can replay it, right? So if another investigation is taking place, and it's a very similar situation to this, where we want to take a look at the children processes and then trace it backwards, we could move that to a function. We could just replay it inline. The idea here is you should be accelerating as you investigate. So one investigation should feed into the next one, right? You should be getting faster and faster every single time. This could also be training material or runbooks. So you have a new person coming into your team. Maybe you had a red team recently. Go ahead and start a new engagement. Have them play through your last notebook step by step and explore that data. Grapl has a plugin system, and I've managed to apply Grapl to a lot of different problems, and in ways that I don't think I ever would have even tried after being burned before and taking clusters down and that sort of thing with other systems. So here you can see an inter-process communication node, which is implemented as a plugin, and this allows me to detect things like SSH hijacking, where a process is performing IPC to an SSH agent or SSH daemon. We can do process tree analysis, so unique parent, unique grandparent processes. Again, this is applied to SSH. We can see like a Python process shelled out to SSH. The nice thing with Grapl is that it's going to stack unique parents and unique grandparents automatically in those lenses, right? So that correlation ends up building up really, really quickly the more unique your process tree is. You can build recursive queries, which I don't actually think other systems even support, but if they did, I think it would be extremely slow. But in Grapl, we can ask questions like, given a process, trace that process tree backwards, and if we see a user ID change in that process tree, we're going to call that a privilege escalation, right? So a simple case of this would be calling sudo and changing users. But if an attacker had some sort of an exploit where they were able to privesc and spawn a child process, as long as that relationship is there, we would be able to catch that. So I'm going to really quickly go over how to set Grapl up. It's designed to be really simple. So you can clone the repository. Grapl is open source. It's free to use. You pull it down, go to the Grapl CDK folder. You have to fill out a .env file with just a bucket prefix. An org name is probably a good idea, something unique. And run the deploy all script. And that's really it. At this point, it's going to set up all of the infrastructure for you. There's really only one more step, and it's pretty simple. Go to the AWS console. Go to the SageMaker notebook section. Grapl will have already created a notebook for you, so you can just open that up. Upload or use the Grapl provision notebook, and just hit the play button, and it's going to set up the database schemas. It's going to set up a user for you. You're good to go at this point. You can send up the demo data. It's in the repo as well. And that's really it. So I'm working full-time on this now. Grapl's open source. I'm certainly curious to hear any feedback that people have. There's a Slack channel, or you can just hit me up on Twitter. Always happy to hear feedback about it. Cool. We got a couple minutes for questions? Cool. So, got one over here.
Have you gotten any interest from vendors in integrating Grapl?
Yes. I don't think I could probably say a lot more. But yeah, there's definitely interest from, everyone has these problems. Vendors have these problems, security teams have these problems. Lots of vendors are drowning under their data the same exact way that security teams are, and there's definitely interest there, yeah.
In your example with cron, would you lose the trail because you have a bunch of people writing to cron and then cron spawning a bunch of things, or can you trace whose cron is whose?
Yeah, so with the right instrumentation, we could definitely trace it. If the data is not being provided to Grapl, then you might have to do like a little work to say like, show me all of the possible places where the cron may have been set or where that may have come from. But the nice thing is that if you just fit that instrumentation there, you'll automatically get that, right? You won't have to do any manual work. It'll just sort of be there. Yeah. Question over there?
So what kind of log data does it ingest? Like, you did a lot of Windows stuff. Like, is it like syslog data? Is there a bunch of standard formats?
Yeah, so there's two, what's that? Oh, sure, so the question was, I showed a lot of like Windows stuff. What other data sources does Grapl support? I think that's like a, yeah. So right now, Grapl, the version that's in the repo supports two data formats. One is sysmon, so it'll just natively work with sysmon. The other is just a generic JSON format. So if you can map your logs to that format first and send it up, you'll get things like process and networking and file work all for free. If you wanted to have custom parse data, you can build parsers in Grapl. You can extend the whole thing arbitrarily. So if you wanted to do that, we should definitely talk. But I have done, like the SSH stuff was on Linux. My colleague is working on an AWS plugin that'll let you ingest things like CloudTrail. So really, it's arbitrary. You can bring your own model. Yeah, and we've got one in the back over there. Yeah. So cycles are fine. They're probably so the Python code you saw is going to compile down to a graph query language, and it's going to handle resolving cycles for you. So if there's a cycle in there, it'll detect it. But cycles are natural, right? A process might create a file which executes as another process, which IPCs back to that parent process, right? So it has to handle stuff like that, and there's work in there to do it. Yeah. Any other questions? Oh, yeah.
GraphQL search existing libraries and systems were you able to take advantage of in building Grapl?
So Grappl's built off of a graph database called dgraph, which has a very GraphQL-like query language. It's at least inspired by it. I think they now support GraphQL natively, so you could, if you wanted to build your own Grapl analyzer library, you could build it on top of GraphQL. Or if you want to just use pure GraphQL, you could do that in Grapl. I believe today, I think it's on a version early enough or new enough to support full GraphQL. Yeah. I think that's it. Cool. Thank you.
Thank you. And thank you for speaking. That
Thank you.
appreciate you. Thank you very much.